Dear students, welcome to today's lecture in which I am going to discuss some more interesting features of inverse reactions. Inverse reactions. We have started discussing the properties of nuclear reactions in terms of cross sections and reaction rates, and after I had spent some time on the mathematical representation of cross sections and rates of nuclear reactions, I started discussing the importance of inverse reactions. And in the previous lecture, when I started this topic, inverse nuclear reactions, I said at low temperatures, predominantly those nuclear reactions which have positive Q values, they will dominate the synthesis of elements and also the energy produced from the stars. But as star evolves with respect to time and space, the energy available for the particles also goes up, right. So, at high temperatures, because the particles are getting the chance of getting, they are getting the chance of possessing more energy at high temperatures. That means, energy of the particles is much higher than the Q value of the reaction. Then we can expect the inverse reactions also to happen. In general, at elevated temperatures, inverse reactions progressively becomes significant. So, to understand the stellar evolution, which is one of the main objectives of this course, to understand the stellar evolution, it is important to know how these forward and inverse reactions proceed. Okay. So, if you want to understand the stellar evolution in terms of the forward and inverse reaction, what are the parameters we look forward to? Can you think? See, our aim is to understand the energy produced from the stars and the synthesis of elements, which overall comprises the stellar evolution. Now, when it is clear that to understand the stellar evolution, we need to understand the rates with which forward and inverse reaction take place. So, the question is mathematically how to get a better understanding of this, whether inverse reactions rate and forward reactions rate, if we take the ratio of those rates, the ratio will it be sensitive to the Q value? I repeat, the ratio of inverse reaction rate and forward reaction rate, if we consider, whether it will be sensitive to the Q value? If yes, can we get some quantitative information? In terms of numbers, can we try to understand? Not only Q value, the ratio of the reverse and forward reaction rates depends on temperature. If yes, at what temperature it becomes more significant? Qualitative statement I have given that at high temperatures, inverse reactions becomes progressively becomes important. But it is also important to understand this in terms of mathematical expressions, And today's lecture, I am going to discuss this particular point. What is that? The ratio of the reaction rates when we consider forward and inverse reaction and understanding its relation with the Q value of the nuclear reactions and the temperatures of the star. Now, for that we need to write the expressions for the reaction rate, and if I want to write the expression for reaction rate, one needs to write down the expression for cross section, which I have already written in the previous lecture. So, with that I will start today's lecture. Okay. So, the contents of today's lecture are as follows. Recap I have already done, and in the topic inverse reactions, as I said, we need to write down the ratio of cross section of the forward and inverse reactions, and what is the ratio of reaction rates of inverse and forward reaction, and as an example I will discuss photo disintegration if time permits. Okay. And also I will discuss energy production from the stars depending on the availability of time. Otherwise, I will discuss these two topics in the next lecture. Okay. Okay. So, and also I will try to cover lifetime, okay, in this 1 or 2 lectures. So, in the inverse reaction, as I said, nuclei of type 1 and 2, when it undergoes reaction, they give in general nuclei of type 3 and 4, and at low temperatures Q greater than 0 type of reactions takes place predominantly, and at high temperatures, as I said earlier, 3 plus 4 giving rise to 1 plus 2. When this is basically Q less than 0, this can happen, this inverse reaction can happen when the energy available for the particles is greater than or equal to Q value of the nuclear reaction. Okay. If it is Q value positive, one more interesting question, why positive Q value nuclear reactions play important role at low temperatures? Because for the energy liberation, it is always important to have positive Q value nuclear reactions. So, that is the reason at low temperatures you will come across nuclear reactions with positive Q value, they play important role in the energy production. And as the energy increases, and because of various processes, when the temperature of the star increases, particles will get enough energy to induce reverse reaction as well. Okay. And now we are in process of understanding the ratio of the reaction rates. Before that, we need to write down the expression for the cross sections, right. In the last lecture, if you remember, the cross section of nuclear reaction, when we consider this particular case, okay, is there are four terms involved. Number 1, a term which describes the quantum mechanical character of the nuclear reaction. I think I have given enough information why pi r square, which is the geometrical cross section in classical case, should be replaced with pi lambda prime square, reduced de Broglie wavelength, which has the quantum mechanical character, because the nuclear reaction comes under quantum mechanical processes. Only one term is sufficient, 3 more terms are important to include in the expression for cross section. So, number 2, the statistical factor 2j plus 1 divided by 2j2 plus 1, okay, 2j1 plus 1. To write this, we need to imagine a simplistic case when entrance channel, okay, 1 plus 2 gives rise to a compound nucleus in the excited state whose angular momentum is j and parity pi. Okay. This is the compound nucleus. Fine. It has some energy which is excitation energy, and with this excitation energy the compound nucleus will decay to 3 plus 4 types of nuclei. Okay. This is called as exit channel. Now, J is the angular momentum or angular momentum of the excited state of the compound nucleus, and J1, J2, they are the spins of the nuclei of types 1 and 2. So, what is its importance? This is known as a statistical factor, and this is also represented by a symbol omega. So, from now onwards, whenever I use the symbol omega, please remember I am talking about the statistical factor. Why statistical factor is important, my dear? See, the probability for the reaction to happen, right now I am discussing only the forward reaction, right, only forward reaction. The probability for the forward reaction to happen increases if the number of final states available increases. What does it mean? 1 plus 2 is giving rise to 3 plus 4, but depending on the conditions in which this nuclear reaction is taking place, we can get 5 plus 6, 7 plus 8, okay, 3 plus 6, any combination of the nuclei types in the exit channel can occur with what probability? That is where this statistical factor comes into picture. Let me rephrase this statistical factor concept. The probability for the nuclear reaction to proceed in forward reaction goes up with the number of final available states increases, okay? And you know from quantum mechanics that any energy state with angular momentum j will have 2j plus 1 substates, 2j plus 1 substates. That is the reason I have written it in the numerator. Now, reaction is proceeding through entrance channel, that is 1 plus 2, right, and the probability for the particles 1 and 2, the probability for the particles 1 and 2 to identify in one of the substates is inversely proportional to the product of the substates of J1 and J2, right. What I am trying to say here is the probability of finding the particles 1 and 2 is inversely proportional to the number of substates corresponding to particle 1 and particle 2, okay, 2j plus 1 and 2j2 plus 1. Okay. So, J1 is the spin of the particle 1, J2 is the spin of the particle 2. The product of these two substates is deciding the probability of finding the particles 1 and 2 in one of the substates. So, overall the product of these two probabilities, number 1 2j plus 1, number 2 1 by 2j1 plus 1 and 2j2 plus 1. This product of these two probabilities decides the statistical factor which is represented by omega. So, this physics aspect also must be considered when you try to write a general expression for the cross section. I hope it is clear to you. Okay. We have two more terms. If we need to consider the identical nature of the particles, we have to use the symbol delta 1 2, that is Kronecker symbol, okay. And then fourth term which tells us the nature of interaction, in the whole process. So, number 1 pi lambda square, where the reduced wavelength, reduced de Broglie wavelength has quantum mechanical character in terms of h by square root of 2 m e, right. And second term is statistical factor, third is this Kronecker symbol concept. Number 4, because it is a quantum mechanical process, as I said in one of the previous lectures, cross section of any nuclear reaction depends on the nature of the interaction involved. What does it mean? Whether strong force is involved, whether electromagnetic force is involved or weak force is involved. Accordingly, the cross section varies. Of course, you remember when you go from electromagnetic, when you go from weak interaction to electromagnetic interaction to strong interaction, the cross section increases tremendously. So, do not you think we have to include this topic, we include this parameter related to the interaction? Then how to represent mathematically? That to write that expression, we need to understand that in quantum mechanics, if a few steps are involved in the quantum mechanical process, each step is represented by a matrix element. Each step is represented by a matrix element. How many steps are there in this process? See in this diagram. Transition from entrance channel to the exited state. Transition from entrance channel to the exited state. Number 1. So, it is basically a two-step process, right? And second step, transition from the exited state of the compound nucleus to exit channel, where particle 3, particle 4 are formed. Which type of interaction is involved in the transition from entrance to compound nucleus, and which type of interaction is involved from compound nucleus to exit channel? How to represent this mathematically? I am writing here. Okay. So, it is basically 1 plus 2, I will explain in clearly, this H2 and compound nucleus, okay, and C H1 3 plus 4. Okay. So, this is basically the probability. You know the square of some term, the wave function kind of thing in quantum mechanics, that gives information about the probability, right. So, here the square of two matrix elements are there. Number 1, basically it is the other way around. Okay. Let me rewrite this expression, because we are not discussing the inverse reaction, we are discussing the forward reaction. Okay. So, 3 plus 4 H 2 C and C H 1 1 plus 2. So, here this term involves the transition from 1 plus 2. Let me take some other color so that it can be clear to you. So, this term represents the transition from 1 plus 2, that is exit entrance channel to the compound nucleus, and this term tells us the transition from compound nucleus excited state to the exit channel, that is 3 plus 4. Okay. What is this H 1? This H 1 denotes the interaction in the step 1, H 2 denotes the interaction term in step 2. Okay. And this H 1 and H 2, they are called as matrix operators. Okay. The operators which represent the interaction type, if it is weak interaction, if it is electromagnetic interaction, or if it is strong interaction. So, together this product of matrix elements and square of it gives us the probability in terms of cross section that we have been discussing. So, overall the cross section is product of these 4 terms. Okay. So, regarding the 4th term, I repeat, the transition from entrance channel to compound channel, compound state is represented by this matrix term, and this transition is taking place through an interaction. That interaction is represented by an operator called as H 1, and the compound state is going to decaying to entrance channel, that is 3 plus 4 particles, and this transition is happening through an interaction. It could be electromagnetic, it could be weak, or it could be strong force. Through that interaction is represented by an operator called as H 2, because it is step 2. I hope the product of these 4 terms represents the cross section is clear to you. So, with this analogy, can we write expression for inverse reaction? Let us see. Okay. Because ultimately we are looking for the expression for reaction rates of inverse and forward reactions, right. With the same analogy, I can write down sigma 3 4 is equal to pi lambda square 2 j plus 1, because there is no change in the compound nucleus. Okay. For the inverse reaction I am saying, for the inverse reaction at high temperatures, you have to write the statistical factor as 2 j 3 plus 1 and 2 j 4 plus 1, okay, and 1 plus delta 3 4 Kronecker symbol, and here you will write down 1 plus 2, this is H 2, okay, this is H 2, and compound nucleus H 1 3 plus 4, okay, square. Why I have changed here? In this particular case, in the inverse reaction, the entrance channel contains 3 and 4 nuclei types, right. They are giving rise to compound nucleus through an interaction which is represented by this operator. And this second term, if we see the second term, the compound nucleus is going to exit channel 1 plus 2 through an interaction represented by matrix operator H 2. What you can understand from this expression? From these 2 expressions, it is very clear that matrix elements, they are same. Matrix elements, they are same, whether it could be forward or inverse reaction. And in general, the laws governing nuclear reactions, they do not change. They do not change if the direction is reversed. If the direction is reversed, this is called as principle of principle of time reversal invariance. So, according to principle of time reversal invariance, reaction can proceed in both directions. Reactions can proceed in both directions without any problem. And remember, this H1 and H2 need not be the same. H1 and H2 need not be the same. To date, there is no experimental evidence which can say that this is violated. Principle of time reversal invariance is violated, like that we do not have any experimental data, at least for strong and electromagnetic interaction. At least for strong and electromagnetic interaction. So, considering the strong and electromagnetic interactions only, can we write down the ratio of cross sections for forward and inverse reactions. So, how does it look like? So, this fourth term, as I said, dependence of nature of the interaction, and these matrix elements are identical except for the reversed order. So, the processes can happen in opposite direction without any problem. Okay? And this is called, as I said, principle of time reversal invariance. So, in the next slide, let me write down the ratio of cross sections, and no violation has been observed experimentally for at least strong and electromagnetic interaction. Strong and electromagnetic interaction. Now, if we take the ratio of the cross sections, how it looks like, my dear? Sigma 3,4 divided by sigma 1,2. Please remember, the matrix elements will get cancelled. What are the three remaining terms? Statistical factor omega, pi lambda square, and the chronicle symbol. So, considering these three terms, the ratio of the cross section will look like this. Okay? So, it is basically M3 M4, because I am expanding the expression for lambda, and M1 M2 E34 divided by E12 2J3 plus 1 2J4 plus 1 1 plus delta 12 and 2J1 plus 1 2J2 plus 2 1 plus delta 34. So, to get to this relation, the quantity lambda I k square has been replaced with the expression of h cross square divided by 2 mu I k E I k, where this is the reduced mass and this is the center of mass energy. This is the center of mass energy. Remember, they are non-relativistic form. This expression is in non-relativistic form. The interesting thing is that though it is a two-step process, in the ratio of the cross sections, there is no appearance of the compound nucleus property. I mean, the property of the compound nucleus is gone in the ratio of the cross sections. And this shows that if I can measure the cross section in one direction, I can also measure the cross section in reverse direction, provided all these terms are known to you. And one can have good examples and numericals in the assignments you can expect based on this principle of time reversal invariance. Okay. Now, we are in a position to write down the cross section. I mean, we have written the cross section ratio. Let us go for the reaction rate. Okay. For that, let us write down the reaction rate for forward reaction and reaction rate for the inverse reaction, then go for the ratio, and you see at what temperature inverse reactions plays important role. Okay. So, that is the purpose of this lecture. All right. So, in order to arrive at the analogous ratio for the reaction rate, let me write down sigma v 1 2. The general expression for the reaction rate I have already written in the previous lecture. Either you can use mu 12 or m 12, does not matter, and 1 by k T to the power of 3 by 2 and 0 to infinity, okay, sigma 12 E 12 and e to the power of minus E 12 by k T and d E 12. Similarly, for the inverse reaction, this is for inverse and this is for forward reaction. So, sigma v 3,4 can be written as 8 by pi reduced mass when third and fourth type is considered, okay, 1 by 2 and 1 by kT to the power of 3 by 2, 0 to infinity sigma 3,4 E34 e to the power of, the derivation and the rationale behind this kind of expression already have discussed in detail in previous lecture. Okay. Now, when you have the reaction rates for forward and inverse reaction, and when you have the ratio of the cross section, because in the reaction rate I have to write down the sigma 1 2 and sigma 3 4 also, right, and take the ratio of this reaction rates and consider the ratio of the cross sections, one can write down the reaction rate like this: sigma V34 sigma V12 is equal to 2J1 plus 1 2J2 plus 1 divided by 2J3 plus 1 2J4 plus 1. Okay. And here you cannot ignore the chronicle symbol case, okay, 1 plus delta 1 2, and the ratio of the reduced masses mu 1 2 divided by mu 3 4 to the power of 3 by 2 e to the power of minus q by kT, e to the power of minus q by kT. So, because the quantities preceding the exponential order, they are of normally unity. Okay. The terms coming before the exponential, if you see that ratio, if you take, it is normally close to 1. Now, I am giving a very important statement. The ratio of the reaction rates depends on only exponential term, only exponential term. In the exponential term, you have two quantities, q value and temperature, q value and temperature. Now, with this dependence of reaction rates ratio, in the numerator you have inverse reaction, in the denominator you have the forward reaction. The ratio depends on the e to the power of minus q by kT. So, if I increase the q value, which one will dominate? If I increase the temperature, which one will dominate? You can easily have a guess. Just I can tell you some interesting number. If I go for temperature 0.2 to 10, then the ratio, considering a specific q value, it ranges from 10 to the power of minus 51 to 10 to the power of minus 2, 1, okay, 2, 4, 5, if you take all these values of temperature in gigakelvin, okay, and the ratio if you take, it ranges from 10 to the power of minus 51 to 10 to the power of minus 2, inverse reaction divided by forward reaction rate. That means, at high temperatures, inverse reactions play a very important role. I hope all of you have understood what I am trying to say, and in the next lecture, I will discuss more about this based on the reaction rates. So, the purpose of today's lecture is to understand the dependence of the ratio of the reaction rates when we consider forward and inverse reaction, how it depends on the q value of the nuclear reaction, which is the energy liberated in the nuclear reaction. That energy liberated in one nuclear reaction decides, together with all other q values of the nuclear reactions, overall the energy produced from the stars. So, that is why it is important to understand how the two reactions proceed, forward and inverse, and with respect to temperature, how ratio looks like. Thank you very much for your attention. I am looking forward to meet you in the next lecture, when I want to discuss more about the inverse reaction. Thank you so much.